Okay, so now we're going to name the second type of ionic compounds, also known as polyatomic ionic compounds. Polyatomic ionic compounds contain polyatomic ions, and this table 3.7 from your book has a list of the common polyatomic ions. Polyatomic ions are a group of covalently bonded atoms with a net charge. So they're like little molecules, except they have a net charge on them. So they are covalently bonded atoms with an overall charge. So it's really good to have this table on hand because you will need it in order to name the any kind of polyatomic ionic compounds. So anything with more than one atom counts as polyatomic. So Hg2 with a 2 plus on it it's called mercury 1 because really mercury 1 is only exists as this diatomic mercury cation with a 2 plus charge on it. NH4 is ammonium. NO2 minus is nitrite, and NO3 minus is nitrate. Now you'll notice with the ite and the ate, those suffixes tend to apply to polyions that have oxygens in them. And the polyion with fewer oxygens gets the ite suffix, and the one with more oxygens gets the ate suffix. You also see that in sulfite and sulfate. So the one with more oxygens gets the ate suffix rather than the ite suffix. So it's the same pattern. HSO4 minus is usually called actually bisulfate, but they're trying to kind of change the name to hydrogen sulfate for that polyion. OH minus is a hugely important one, hydroxide, strong base, so that's a really good one to know. CN minus, cyanide. PO4 3 minus, phosphate. This is how almost all phosphorus exists on planet Earth. HPO4 2 minus is hydrogen phosphate, and H2PO4 minus 1 is dihydrogen phosphate. You'll notice that most polyions are anions. Very few of them are actually cations. So these are the only two that are cations. The rest of them are anions. Okay, we have a whole bunch of other ones on the right side as well. Let's see, I'm just going to show the really important ones. Carbonate, CO3 2 minus. Bicarbonate, HCO3 minus. Almost nobody calls that hydrogen carbonate, so you'll see it often as bicarbonate. ClO minus, sometimes it's written OCl minus, they mean the same thing, that's hypochlorite. And then ClO2 minus is chlorite, ClO3 minus is chlorate, and ClO4 minus is perchlorate. So chlorine is an atom that can take a lot of different charges, so that's why we have this abundance of different oxoanions of chlorine. Here we have acetate and MnO4 minus, permanganate, and et cetera, down the line. So in order to name polyatomic ionic compounds, it's pretty simple. It's the same rules as binary ionic compounds, really, except you don't use the "ide" suffix. You just use the name of the ion. And the only thing that's kind of important to know is that when there is more than one polyatomic ion, I'm just going to abbreviate that to polyion, you want to use parentheses in the formula. Parentheses. Let me show you what I mean. So if we have calcium nitrate, let's say you have to figure out the formula for calcium nitrate. You know that calcium is an alkaline earth element, so it's going to be in the 2 plus, it's going to have a 2 plus charge. Nitrate, you can find it in the table. Nitrate is NO3 minus. So that is going to be like that. So when these two species come together, you are going to need 2 nitrates for every 1 calcium that you have in order to make a neutral ionic compound. So that means that you're going to have to put parentheses around the nitrate to set it apart and indicate that there are 2 of them. Okay, so those parentheses are really important when you have polyions. Let me give you a couple of other examples. Write the formulas for the following ionic compounds. Magnesium hydroxide, and let's say ammonium phosphate. That's a good example to use some of your skills. Okay, so let's do magnesium hydroxide first. Magnesium is Mg2+. Hydroxide, you can look it up in the table, it's OH-. So when those 2 come together, you're going to need 2 hydroxides for every 1 magnesium. So the formula needs a parentheses to set the hydroxides apart. And again, that's because just to get charge balance, I'm dragging the absolute values kind of down to get the subscripts. You need 2 hydroxides to balance out the 2+ charge on the magnesium. Ammonium phosphate. Ammonium is NH4+. You can get that from the table. And phosphate is PO4 3-. So this is a binary compound in which both the cation and the anion are polyatomic. Totally possible. Now, when these come together, you're going to need 3 ammoniums for every 1 phosphate because you need 3 ammoniums to balance out the 3- charge on that phosphate. So the resulting formula should have the NH4 in parentheses, so I can have 3 of them, and then the phosphate comes after. So the convention is to write the cation first and then the anion in all of these binary compounds, binary ionic compounds. The last category of ionic compounds are the acids. The acids are a special class of compounds that contain an ionizable hydrogen, an ionizable H+ ion. Usually the hydrogen appears first in the formula, but not always. We're going to learn, especially next semester, we're going to learn about situations where the hydrogen does not appear first, but usually for your purposes this semester it does. So there are 2 major types of acids. The binary acids with only a hydrogen and then 1 other element, and the polyatomic acids. So let's do binary acids first, and then we'll discuss the polyatomic acids next. The binary acids have just 2 elements in them, and really you should just kind of know their names. You need to be fluent in them, and the easiest thing is just to remember their names. These include the halogen acids, so hydrogen with all of the halogens. Fluorine, chlorine, what's next? Bromine actually should be next instead of iodine. And iodine. So here we go. And HI. These are the major binary acids. And these take a hydro prefix. Hydro prefix. So I would call this one hydrofluoric acid. I would call this one hydrochloric acid. This would be hydrobromic acid because of bromine, hydrobromic acid. And the other one is hydroiodic acid. Okay. These are halogen acids that you should know. The polyatomic acids usually, but not always, contain oxygen, and they do not take that hydro prefix. So let me give you a bunch of examples of the polyatomic acids. There's a nice table in your book towards the end of section 3-12 that shows these. We have, for example, HNO2, we have these oxygens, and HNO3. We also have H2SO3 and H2SO4. So you can kind of see a pattern in their names. This one is, oops, that's too thick. This one is nitrous acid, and this is nitric acid. So the us goes with the one that has fewer oxygens, and the ic ending goes with the one that has more oxygens. So applying that same logic to these two, this one is sulfurous acid, and then H2SO4 is sulfuric acid. Okay. What's another example? Another example is H3PO4. This one, again, you just have to know this. Look at the table and kind of try to memorize the names of the acids. The H3PO4 would be phosphoric acid. That's the only one with a phosphorus oxoanion. So it's good to know those acids because they're special cases. Even though they're binary, they're named as acids with these kind of special names that you have to know. So that concludes our discussion of naming ionic compounds.